This video is going to be about the ambiguous case of the sine rule. Why do we need this? Well, it turns out that from the same initial information, you can sometimes draw more than one triangle. So first of all, let's look at this situation we've got here. We've got to work out whether we can actually draw a triangle with these dimensions. So we have 30 degrees in the corner. So we're going to label this A in the normal way, and we're going to label this B, and we're going to label this angle C. Okay, so we've got a situation where obviously A is 30. The opposite length to A we need to be 4, so we're going to call that A. And opposite length to B, small b, has to be 10. So the question is, can we draw a triangle with these dimensions? Now I've put this into GeoGebra, and you can see that it's not possible to draw a triangle with these dimensions because the opposite length to A is not long enough to reach the bottom. So let's see if we can work out how long A would have to be so that there would be a solution. So if we go back to our diagram, so how are we going to work out what that is? Well, we know that this cannot be 4 as it is shown here. Now the shortest length that it can be is when it's a right angle triangle. That'll be the shortest distance so that it actually reaches the bottom. So what we can do is we can work out that length. So let's call it H. It's the height of the triangle. So we can see that this is just a right angle triangle, so we can see that sine of 30 is opposite over hypotenuse. So if we rearrange that, 10 sine 30 is equal to the height, and actually sine of 30 is 0.5, so it's equal to 5. So it's showing us that actually for anything less than 5, it's just not going to reach the bottom. So let's go back to GeoGebra, and we can look and see what happens here. So I can increase the value of A. So let's see what happens. I'll increase it, and you can see, oops, we got to 5. Then yes, you have the right angle triangle, and you can draw it. Anything less than 5, obviously it's not going to reach. There's going to be no solution. Okay, so let's see what happens now when A is increased to be more than 5. Let's say 6. So I increase it to 6. Now you can see that in this case, actually, there are 2 different triangles that you can draw, both of which have A is 30, the opposite length is 6, and length B is 10. There's 2 different possibilities. ACB1 and ACB2. So you can see they have the same information, but they're looking completely different. And in fact, the length of C at the bottom length of the triangles is completely different, and the angles inside are going to be very different as well, apart from the 30. Okay, so the question is, what happens if I go even further now? So you can see we keep having these 2 triangles. I'll just zoom out a bit. But what's going to happen when I get to a certain point, you can see that the triangle is getting bigger and bigger and bigger. But when we get to 10, so in other words, isosceles triangle, you can see we're back to 1 solution. And if you go bigger than 10, you can see you can only ever make 1 triangle because it can't go back on itself. So let's go back to that. So if we anything, so the conditions for the different number of solutions in this case, anything less than 5, there's no solution. When it's equal to 5, we have one right angled triangle. Then between 5 and 10, there's always these two different triangles you can draw. And when you get to 10 or greater, then there is only one triangle again that you can draw. Okay, let's have a look at an example. So I've chosen this one that we were looking at in GeoGebra. So again, this is 30 degrees. B is going to be 10, and the opposite length has to be 6. So we can see that we can either have this triangle, the larger one, this length being 6, or we can draw the 6 the other way and have sort of a smaller triangle inside. So there's two possible triangles, but let's just ignore this one for a minute and just imagine we were given this diagram, and we're looking for this angle to be angle B. So we're looking for this angle B. So this is a classic case of the sine rule. Obviously you have two pairs of angles on opposite sides. So we would do sine of B divided by 10 equals sine of 30 divided by 6. Now sine of 30 is actually 0.5, so 10 times 0.5, that's 5, so it's actually 5/6. Now if we go to the calculator to work out what B is, so obviously we would do shift sine sine of 5/6. Okay, so 56.4 approximately. Okay, so that tells us that this angle, and obviously that's an acute angle. Now, how are we going to find the other angle? Well, the other one is going to be this inner triangle. Obviously also has the opposite length of 6, and obviously this one here, this triangle inside, is actually an isosceles triangle. So we now know that this is 56.4. So obviously, because it's an isosceles triangle, this angle outside must also be 56.4. So the angle inside, because it's on a straight line, so it must add up to 180. So the other solution is 180 minus 56.4. So 123.6. So that always 180 minus the first solution will give you the other solution. Okay, so I'm going to go through the answers here. Now, in the first question, what we need to do is to drop a perpendicular down and find the shortest distance from the top to the bottom. So let's call this H. So we can see if we the connection between these is obviously sine, because sine of 42 is H over 8. Okay, so obviously if we do 8 sine 42, it will give us H. So if I do that on the calculator, so it's 5.35. So basically the shortest length that you can have for this opposite length would be 5.35. So we have a 5 here. So obviously it's that smaller, so it's not possible to draw this triangle. Okay, because it's small, because 5 is smaller than 5.35, and 5.35 is the shortest distance you can have for that. Okay, so here we have the situation, and we can see that we've got these two possible triangles because the 11 is less than the 12, yeah, and we'll just assume this time that it does actually reach to the bottom, yeah, so you can draw it. So obviously what we need to do is to use the sine rule. So we're looking for this angle, or this one here. So let's do the triangle around the outside first. So what we've got is obviously with sine of b over 12, sine 65 over 11, there's the pairs. So I'm going to work out what that is. Okay, and now I just need to do shift sine, or sine to the -1 of that to find the angle. Okay, so it's 81.4. Now, from what we've been saying, this angle over here, this one we're looking for, we said it's always 180 minus this one. Oops. Okay, so the angle is 98.6. Yeah, so they're the two possible answers. Now, for the second part, we've got to actually work out the length of C, which is this. Yeah, so in the first triangle, it'll be the C will be this length, and in the other triangle, the C will be this length. There'll be two possibilities. So if I consider the larger triangle, the one around the outside, where this was 65 and this angle was 81.4, and we're looking for this length, then we can, of course, first of all work out the missing angle at the top. So what I'm going to have to do is 180 minus these two angles, so 65 and minus the 81.37. I'll just do a few more decimal places. So we get it a bit more accurate. So that'll be 33.62. So if I'm looking for C, let's use the sine rule. So C over sine of that angle. And we now have two pairs, but it's easier probably to use this one. It's nicer numbers. So this is going to be 11. And then we just rearrange that. So let's work that out. Actually, it's going to use answer here, so I'll get it a little bit more accurate. And delete those. Okay, so I've got that divided by sine 65. Okay, so this one would be 6.72. And of course then I would have to do the same for the other triangle. So let's do that in blue. Now the other triangle obviously looks more like this. And again, 65 But this time, this one was the 98.61. So I need this angle at the top. So I'm just going to do the same thing that I did before. So 180 minus 65 minus the 98.6. Okay, so that gives me the angle at the top of 16.37. 38 actually. So then I go through exactly the same calculations that I just did. So obviously on my diagram that's 11 as well, and this is 12, but we don't need that. So we've got this pair again. So it's exactly the same calculation. So I'm just going to kind of rub it out. So in this time though, the opposite angle is the 16.38. Whoops. Yeah, so I just need to change this part of it. So let me do that then. So again, I'll use answer. Okay, so I get 3.42. So quite different to the answer we had before because we got these two different triangles. Okay, and the third one, we've got to work out angle B. Now, hopefully you realise that actually there's only going to be one answer here because this 10 is bigger than the 8 we've got here next to the angle. So we should only get one angle. And I'll show you actually what happens if you don't realise that there's only one angle. What happens if you kind of carry on. So in the normal way that we do sine, so sine of B over 8 is sine of 50 over 10. So then we work out sine of B is 8 sine 50 divided by 10. And then we can work out what B is on the calculator. So shift sine. Right, so B is 37.8 basically. Now we kind of realised there's only one answer, but what if we didn't realise that there was only one answer? Well, let's see what would happen. Now what you would do is you'd say to yourself, oh, the other answer must be 180 minus 37.8. So let's do that. 180 minus that. So we might think that there's another angle of 142.2. Now, but the problem here is if you look at that, if that was one of the angles, can you see that this angle over here is 50? Now, if you add those two together, you've already got more than 180 degrees. So it definitely wouldn't work. So if you're not sure and you actually work out the other angle, just check that it's possible for the angles to add up to 180. If it is, then you'll be fine. But in this case, you can see that the angles will definitely add up to more than 180, so it's never going to work. So there's only one possible answer for B in this question.